Sure, so I will. Good morning, everybody. Welcome to a wonderful morning of Chem 1105 with your host, me, Dr. White. All right, remember, a week from this Friday is test number 2. It's a lot harder than test number 1, and that's why I've given you extra time to study. Now, today I'm going to do the practice problems for part 1. There are 2 different parts of the part 1 practice problem that I'll be doing. Now, I can't remember if I already did one. I don't think I did. If I did, let me know I've already done it. I had a class once where I was going through a problem set that I forgot I'd done a couple of days earlier. And it wasn't until about 20 minutes, someone said, you already did that. Wait, come on, you should have told me up front. All right, let's get going. All right, thumbs up, people. Have I done this before? Or better yet, I'm going to do a poll. Instead of saying the question, are you done? The question is, have I done this? Yes or no? Oh, it's 50-50. You know something? I'm going to do it again, even if I did it. Practice is good for your grade. So let's do it. Now, before I do this, I have to open another file. And you all should see on your screen right now, hold on. Now you should see test 2, important information. I highly recommend you look at this, because these are things in the past I used to make students memorize, but now I'll give it to you. But I will expect you to know how to use this stuff. And let's look at the first 2 lines right here. 1 mole of an element equals Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd atoms of that element. And 1 mole of a compound equals Avogadro's number. That's 6.02 times 10 to the 23rd molecules of that compound. So if we go back to the problem set, if we look at number 1, how many molecules are 6.22 moles of hydrochloric acid, HCl? What are we being asked to find? Molecules of HCl. What are we given? Moles of HCl. So this is all we have to start with. What units do I want my answer to be? Molecules of HCl. And therefore, I'm going to use my good buddy, my good friend, unit analysis, and moles of HCl go on top of a ratio, or molecules of HCl, excuse me, and moles of HCl go underneath. And where do we get these numbers? From the following. 1 mole of a compound equals Avogadro's number of molecules of that compound. And therefore, 1 mole, 6.02 times 10 to the 23rd molecules. 1 is exact number. Avogadro's number, we're using 3 significant. This is 3 significant. When you multiply and divide, you get the same number of significant figures as the number you're multiplying and dividing that has the fewest. And when we do that, our answer is this, which is also 3 significant figures. Now, if we look at number 3, how many? Well, let's do number 4. And there's a reason why I want to do number 4. I'll tell you in a little while. How many moles are 8.222 times 10 to the 17 molecules of oxygen gas, O2? So we're trying to find moles of O2. We're given how many molecules of O2. This is the only number we have to start with. And therefore, this is what I have. What do I want my units, my answer to be? Moles of O2. Use unit analysis. Your good buddy, your good friend, whatever you're trying to get to goes on top of the ratio, mole O2. And whatever you're trying to get rid of goes underneath. You don't want molecules of O2 in your answer, the units, so that goes underneath. And where do we get this? 1 mole of a compound equals Avogadro's number of molecules of that compound. And Avogadro's number is 6.02 times 10 to the 23rd. And if we put that in here, we have 6.02 times 10 to the 23rd. Now notice this is 4 significant, exact number. Oh, and Avogadro's number is 6.02, which is 3 significant figures. Actually, the whole number is 6.03 times 10 to the 23rd, but the power never plays a role in significant figures. So my answer should be 3 significant figures. And it's time for Dr. White to share the fun. And the question is, I don't know, say sometime in the future, you might say 5 points. How many moles of nitrogen gas, N2, are 9.73 times 10 to the 33rd molecules of N2? And it's your turn. Have fun. And remember, tomorrow is, this whole week is, turn on your webcam if you have one for Dr. White. Wow, that went over like a lead balloon. Oh, look out. It's time for some old jokes from the past. Generation gap jokes. And when something doesn't go over well, one joke or refrain was, that went over like a lead balloon. Or that's as funny as a screen door in a submarine. Do you get that? And finally, one you will not understand. That's as funny as a flood in a physics factory. Oh, fond memories from my childhood. You can Google physics, F-I-Z-Z, and I'll let you figure out how to spell the rest. All right, it's do not answer the poll question day. Oh, the votes are coming in. Oh, that reminds me. Shh, don't tell anybody, but some people, for their senior prank in high school, got 2 cases of grape fizzies and put them in the swimming pool of our high school. Boy, was the principal upset. That was an understatement. Shh. He's probably unfortunately dead now. He was a nice guy. All right, let's get to work. What are we being asked to find? How many moles nitrogen? What are we given? How many molecules nitrogen? Ooh, Dr. White's getting serious. Oops, forgot the E there. And this is the only thing we have to start with, so I'm going to start with that. If I had a ratio, what units do I want my answer to be? Well, we figured that out. And now I'm going to use my good buddy, my good friend, unit analysis, whatever we're trying to get to. Units goes on top of that ratio. Whatever we're trying to get rid of goes underneath. I'll write them in. And where do we get these numbers? Well, if you look at important information, test number 2, in the past, you'd have to memorize this, but thank you, Dr. White. You don't have to because of the kindness of me and also the fact I realized I should test chemistry, not your memory. All right, 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd molecules of that compound. And that's where you get the numbers that go in there. And now we know for every 1 mole, there's 6.02 times 10 to the 23rd molecules. And now check my units. Notice molecules N2 divided by molecules cancel out because anything divided by itself becomes the number 1, meaning it's canceled out. And I'm left with the right units, moles. And now I'll pick up my calculator. And by the way, come to my office hour tomorrow night if you don't know how to use your calculator and scientific notation. And my calculator gives me this amazing number, amazing because and if you write that down, I'm going to take off a point on test number 2 because it'll say, please use proper significant figures for all calculated answers. And this is 3 significant figures. All non-zero numbers are significant. 0 after decimal and also confined. So this is 3 significant figures. And this is an exact number, which doesn't play a role. Therefore, round this off to 3 significant figures. Your turn. Yeah, 10 seconds. Time's up. Keep the 1, keep the 6, keep the 1. Use this number to round off. That's 5 or higher. I'm going to drop all this after that. And that number 2, increase that by 1. And that's how many moles of N2, 1.62 times 10 to the 10th moles of N2. Now let's move on. And I should mention, I'm going to even do it full screen. Remember, there's no such thing as a dumb question in my class, in my life, ever. I practice that. You should know that by now. When I'm doing this problem set, if you want me to do one I'm not doing, ask and I will. We've got all morning. I've got you. All right, let's move on. And next thing is, what's the molecular weight of a compound? And if we look at number 5, what's the molecular weight of hydrobromic acid, HBr? What's the molecular weight? Well, if you look at test number 2, important information, the molecular weight is the sum of all atomic weights in that compound. So if we look at the molecular weight of hydrobromic acid, remember on test 2, it will say, please use 3 significant figures for all atomic masses. Hydrogen is 1.01 to 3 sig figures, and bromine is 79.9. And you add them up. And when you add things up, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. So if you look at 80.91, you keep the 9 because this has 1 past the decimal, this has 2, and 1 is less than 2. I hope you all agree. And therefore, this should have 1 past the decimal. Keep the 9, use the 1 to round off. It's 4 or less, drop it. And therefore, the molecular weight of HBr is 80.9. Now, let's look at number 7. How many moles are 45.33 grams of sodium chloride? Well, what do? Well, in case you forgot, you go to test number 2, important information. And wait until I clean this up a little. Cleaned up. And you see 1 mole of a compound equals the molecular weight of that compound. And we just determined the molecular weight of that compound is the sum of all atomic weights. So if we go back to our problem, and first of all, what are we being asked? How many moles sodium chloride? Don't forget that's table salt. If you ever go out to dinner, lunch, or breakfast with a bunch of chemists like me, one of us will always ask, please pass the NaCl. Never mind. But anyways, we're trying to find moles of sodium chloride. We're given grams of sodium chloride. Here's what we have. We're trying to get the moles of sodium chloride. Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. Where do we get the relationship between a mole of a compound and the weight of a compound? 1 mole equals the molecular weight. Well, we now have to figure out the molecular weight of sodium chloride. 1 sodium, 1 chlorine, 3 significant figures, 58.5. This is 4 significant, 3. Therefore, our answer, 1 is an exact number, is 3 significant figures. And now I'm going to share the fun. Here's one for you. And since you don't have a periodic table in front of you, maybe, I'll help you out. The atomic weight, hydrogen is 1.01, oxygen 16.0. And it's your turn. Have fun. And when you're done, give me a thumbs up, or I'll take a poll in a little while. But for now, if you're done, give me a thumbs up. I might have said that a little too quickly. If you don't have a calculator, just set it up. Well, by the way, if you're not done, you can say no. I can relaunch the poll when you are done. Spencer, sorry to hear about your calculator problem. The only PC program I know of is Excel. Do you know how to use a spreadsheet? Just make sure when you format the cells, you format it in scientific notation, and you also put a number like 6 or 7 past the decimal so you can round off properly, like your calculator would give you a lot of numbers. And if you don't know how to do that, come to my office hour. I'll be more than happy to show you. Oh, that reminds me. Back when computers were new, yes, PCs, I was the first one in my company outside of accounting. This was an international company, AXO, then called CHEMI, that got an IBM PC Boy, were the other section that had jealous, like little kids. Oh, how come he can get a nice toy and I don't? Well, I was one of the first outside of accounting to learn how to use spreadsheets. That was before even Excel. Or if you want, buy one of these for about $15. And get the solar one. You don't have to worry about a charger. All right, let's get to work. What are we being asked to find? How many grams of water? What are we given? 4.311 moles of water. And how do we proceed? Well, this is the only number I have. I had some ratio that I can multiply this unit by. What unit do I want my answer to be? Grams of water. Oh, excuse me. And now I'll use my good buddy. Oh, I haven't done it this morning. Now I'll use my good buddy, my good friend, unit analysis. I love that whistle. I hope you do too. If not, send me a nasty email. Stop doing that. All right. How do we use unit analysis? Whatever we're trying to get to, the units go on top of the ratio. Whatever we're trying to get rid of, the units go underneath. And I'll put those units here. And where do I get a relationship between moles of a compound and grams mass of a compound? And if you look at important information, test number 2, the 1 mole of a compound equals the molecular weight of that compound, and the molecular weight is the sum of all atomic weights of that compound. And now I need the molecular weight of water, which we've done. So I'm going to go through this real quick. Add the sum of all atomic weights. This is 2 past the decimal, 1. This is the smallest number. Round this off to 1 past the decimal. To the right, keep the 0. Use 2 to round off. That's 4 or less. Drop it. So for every 1 mole equals the molecular weight of water. Now, this is 4 significant figures. This is 3 significant figures. This is an exact number. Therefore, which of those is the smallest significant figure number? 3, and that's what our answer should be. Oops, I forgot to do something. Notice moles of water divided by moles of water cancel out, because anything divided by itself equals the number 1. And now I'll put in and my calculator gives me this number. And I'm going to round that off to what? 3 significant figures. I'll give you 3 seconds to do it first, then I'll do it. Bonus time. Time's up. 1, 2, 3. This is the number to round off. Is that 4 or less or 5 or higher? It's 5 or higher. So I'm going to drop that, increase that by 1. And this is my answer. Now, quick word to help you out on any of my tests, especially upcoming test 2, show your work. If you had pressed the wrong buttons on this, and that happens, I've done it, You've seen me do it this semester once already. You'll get the wrong answer. If you don't show any work and put down the wrong answer, I'm going to give you a 0. If you had all that set up and you get the wrong answer, I say, oh, you must have pressed the wrong buttons. That's a math error. And if it's 8 points, I'll just take off 1 point as opposed to 8. So show your work. Let's continue on. Have you noticed I have a lot of practice problems for you to do? And you should do these on your own because that will ensure you'll do good on test number 2, which I'm assuming, even though you shouldn't assume in life, that all of you do want to do good on test number 2. All right, let's go to practice chapter 5, part 1, mole practice problems, part 2. And let's look at the following. For the following reaction, C2H6O, that's called ethanol, that's in gasoline, that's also the active compound in beer, wine, and hard spirits. You know, the good stuff. You know, Monday was, I think it was Monday, was yesterday, National Vodka Day. Dr. White enjoys his vodka. But only on the weekends. All right. So if we take ethanol, react it with oxygen to make carbon dioxide and water. It's called combustion. I'll teach you more about this later in the semester. If you react 5.00 moles of C2H6O with an excess of oxygen, how many moles of water are produced? So we're trying to find moles of water. We're given moles of ethanol, C2H6O. And when you have excess of something in this class, you can forget about it. So I will. So the only thing I have to start with is 5.00 moles of C2H6O. I want to get to moles of of water. Sorry about that. And I'll use my good buddy, my good friend, unit analysis. And whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath the ratio. And where do I get these numbers? This is important. This is one of the few things I'm going to ask you to memorize. The coefficients, the number in front of the formulas in a balanced chemical equation give you molar relationships. The coefficients in front of the formula of a balanced chemical equation give you molar relationships. When there's no number, like in front of C2H6O, it's 1. And what this really means now is 1 mole of C2H6O reacts with 3 moles of oxygen gas, O2, to make 2 moles of CO2 and 3 moles of water. So for every 1 mole of C2H6O, I make 3 moles of water. These are exact numbers, 3 significant figures. My answer is 3 significant figures. Again, the coefficients for balanced chemical equations are molar relationships or molar quantities. All right, let's look at the following. You're given a balanced chemical equation. And the question is, how many moles of chlorine are needed to react with an excess of sodium to make 1.013 moles of sodium chloride? Your turn. Or as I like to say, start working. Please get to work. Don't forget to vote. All right, let's get going. All right, so the first question is, what are we being asked to find? How many moles of chlorine? And what are we given? Well, we got an excess of sodium, so I can forget that. But we're trying to make 1.013 moles of sodium chloride. And don't forget, you're also given a balanced chemical equation. So now, this is the only number I have to start with. And if I had a ratio, what do I want the units of my answer to be? Well, we took the time to figure that out, and that's moles of chlorine, CO2, chlorine gas. And now it's time to use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. I'll write those in. And where do I find a relationship between moles of chlorine and moles of sodium chloride? I look at the balanced chemical equation. And this tells me for every 1 mole of sodium, 1 mole of chlorine, you make 2 moles of sodium chloride. And because the coefficients, the number in front, gives you molar relationships. And this one, 2 moles of sodium react with 1 mole of chlorine to give 2 moles of sodium chloride. Now, remember when there's no number in front, like in chlorine, Cl2, it's 1. So for every 1 mole of chlorine, we make 2 moles of sodium chloride. And remember, this is an exact number, and this is an exact number. So the only number that will determine how many significant figures our answer should have is that. How many significant figures is that? I'll give you 5 seconds to figure it out. Time's up. 4 significant figures, all non-zero numbers. Zeros after a decimal are significant, and also zeros combined between non-zero numbers are significant. So this has 4 significant figures. My answer should have 4 significant figures. And now I can look at my units and know moles of sodium chloride divided by moles of sodium chloride cancel out, because anything divided by itself equals number 1, meaning it's gone. So now I can turn on my calculator, clear it. And my calculator gives me this number, which is 4 significant figures. And I'm done. And that's how you do it. Now, if I look at the clock on a long morning like Tuesday, hopefully not too long for you, it's time to take a break. It's now come back at 9:50 in about 5 minutes, a little more than 5 minutes. Don't tell anybody, giving an extra 25, 30-second break. And I'm going to go stretch, and we'll come back, and you'll still get out early this morning. Yay, Dr. White. But you're going to learn a lot too that'll help you on tests and other things. So I'll see you in about 5 minutes. Time to get started. All aboard. All right, are you all back? Give me a thumbs up if you're back. No, you don't have to. Boy, this is the anti-thumbs up class. All right, let's get back to work. And let's look at number 4 of that same problem set. And here you're given a balanced chemical reaction, C3H8, that's propane. That's the stuff you find in the white tanks for your barbecue. React with oxygen to make carbon dioxide, water, and you don't show it here, but you also get heat. And that's called combustion. That's how you cook things on your barbecue if you have a propane barbecue. No good one like a Weber. But anyways, the question is, how many grams of C3H8 propane are needed to make 24.6 grams of CO2? So what are you being asked to find? Grams of C3H8 propane. What are you given? 24.6 grams of carbon dioxide. Listen carefully. There's no way in one step that anyone can go from grams of CO2 to grams of propane. Now you can set it up where you have a couple steps merged together, but that's not truly one step. So what do you do if you want to go from grams of one compound to grams of another? By the way, something I didn't put here was 10 points. And now we look at important information, test number 2, mass calculations, which mass means grams. And it's 3 steps. And this is going to be given to you. In the past, students had to memorize this. No longer. So step 1, whatever you're given in grams, you convert to moles. Then what the moles you just calculated, moles of A, you convert to moles of the answer you want to get, B. But you're trying to get the grams, so you go from moles of B to grams of B. Remember, this is grams, this is grams. So let's look at how we do this. Step 1, I want to go from grams of A, what I'm given, CO2, to moles of A. Well, here's the grams. I want to get the moles. Use unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. Where do we get these numbers? Test number 2, important information. 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. So in order to proceed, I need the atomic weight of CO2, because 1 mole of CO2 equals the molecular weight. Did I say atomic weight? I meant a molecular weight. And it's 1 carbon, 2 oxygens, and here's the calculation, and it's 44.0. And now we do the math. Grams of CO2 divided by grams of CO2 cancel out. We're left with moles of CO2. This is 3 significant figures, exact number 3. And this would be the number. Now, when you have a multi-step calculation, there are 2 types of philosophy, how to round off. I'm a round off at each step person, and I do. And there are others who wait till the end. I'm not going to force you to do the way I do. If you want to round off at the end, that's okay. And I'll calculate it both ways, rounding off at each step and tea time. rounding off at the end. And either number, if they're different, will be correct. Now, we have moles of CO2. We're trying to get the grams of CO2 of C3H8. Now we do step number 2, moles of A to moles of B. In this case, moles of A is the moles of CO2 we just figured out. We want to get the moles of C3H8. Use your good buddy, your good friend, unit analysis. Moles of C3H8, propane goes on top. Moles of CO2 goes underneath. Where do I get a relationship between moles of C3H8 and moles of CO2? From the balanced chemical equation. Remember, when there's no number in front of the chemical formula, it's 1. And this balanced chemical equation tells me 1 mole of C3H8 makes 3 moles of CO2. And because that's what we need. So 1 mole of C3H8 makes 3 moles of CO2. Remember, these are exact numbers, 3 significant figures. My answer is 3 significant figures. Are we done? No, we're trying to get to grams of C3H8. Therefore, we need step 3, our final step, yay. And that is moles of what we just figured out, B, in this case, C3H8. We go to grams of C3H8. So I have moles of propane, C3H8. Want to get the grams of propane. Grams goes on top of this ratio. Moles go underneath. Where do I get this? 1 mole of a compound equals the molecular weight of that compound. And the molecular weight of C3H8 is the sum of all atomic weights. 3 carbons at 12.0, 8 hydrogens at 1.01. Do the math, remember, round off properly, and you get 44.1. Put it in there, 3 significant figures, 3 exact number. And the answer, if you round off at each step, is 80.80, what am I saying? 8.20 grams C3H8. Now, if you're a round off at the end person, which is allowed, you would get 8.22. So either answers are acceptable on my test and would be correct. Now, since I just recently went through this a couple of times, I'm not going to do any more problems like this. You can go and look at them on your own. Are there any questions on Chapter 5, Part 1? Now's the time to ask. I should look up here because that's where my speakers are. By the way,
I got a question.
Go for it.
Yeah, so you know how the last problem that you just showed us, that final answer that you got, do you divide the molecular weight and then the mass or whatever? I wasn't sure how to.
Let me go back and do that again. That's a great question. Thank you for asking your question. Is this the one, step 3, you want to look at again?
Yes, sir.
All right. Now, notice we have moles of propane, C3H8, and we want to get rid of that. We don't want, so we're going to divide in our ratio by moles of C3H8. On top, we have the molecular weight, grams of C3H8. Now, how do we get that? By using unit analysis. This goes on top, grams of C3H8. And because of that, your question was, which goes on top or bottom, grams or moles? Use unit analysis. That leads you to the right way. You don't have to memorize anything other than what you're trying to get to goes on top of the ratio. What you're trying to get rid of goes underneath. Therefore, grams of C3H8 in step 3 has to be on top in order to be in the final answer. Does that help you?
Yeah.
Good. If not, I'd explain it again, because sometimes I may not do a good job explaining. I try to, but The last time I checked, I don't walk on water unless it's frozen. Even then,
Did you get that 8.20?
for this one, I got 8.20. Yes.
Okay.
Hopefully I did my math correctly. If I didn't, let me know. Even then, once in a while, I do make mistakes on problem sets. I'm human. Oh no, I gave away a secret. I bet you thought I was a Vulcan like Spock. Oh, by the way, how many of you know Star Trek or familiar with it? Let me do a. Give me a thumbs up if you're familiar with Star Trek, the original one, or any of those. I see some Trekkies out there. I am too. I remember when it first came out when I was in, I think, high school, when Star Trek, the first one, TV program. And it's time for me to teach you a little something. If you haven't figured out by now with my gang gesund, I'm Jewish. And if you ever go to a temple, I do, at the end of a service, the rabbi blesses the congregation. And he holds his hands out like this. And that's the Hebrew letter Shin. And that's standard. Well, Leonard Nimoy, who played Spock, they needed some sort of symbol for something for a greeting. And he remembered from temple, especially it impressed him when he was a little boy, the rabbi would do this. And that's the Vulcan greeting, which is really from the way the rabbi holds his hands in blessing the congregation. Now, the other thing, a lot of the original Star Trek TV program plots are based on morals from the Talmud. If you don't know what the Talmud is, look it up in Google. All right, since there are any more questions on chapter 5, part 1. I bet you never thought you'd learn all these great things about other things besides chemistry from your host, me, Dr. White. All right, it's lab time. And today's lab uses some of the stuff we learned today. Let me just close up a few things. All right, I think we're about ready to go. All right, have you ever wondered how they came up with water's H2O? How come it's not H5O7 or any of those other things? Or how about sodium chloride? Pastanacle is 1 chlorine, 1 sodium, NaCl. Or other things like calcium chloride is CaCl2. How did they come up with that? Well, a long time ago, chemists went into the lab and determined that using experiments. Yes, really. And today you're going to do the same thing. You're going to determine the chemical formula of magnesium oxide, otherwise known as the empirical formula. Now, there are different types of formulas, and I'll teach you later on about actual structures we use in organic chemistry. Remember, I'm an organic chemist. And let's look at today's lab. And today's lab, it will be done in Beyond Lab Dr. White. In other words, we're not using Beyond Lab Z today, but we will be doing it, I think, next week. It'll be a lot of fun. But anyways, how do chemists determine empirical formulas of key inorganic molecules? They use chemical reactions and the mole concept, which we just practiced today. In this lab, you'll determine the empirical formula, magnesium oxide. If you notice, I didn't give it to you. I have MgXOY. And magnesium oxide, MgXOY, is made by reacting magnesium metal with oxygen in the air. And you will determine from today's lab is what is X and what is Y in the formula for magnesium oxide, MgXOY. It's not X and Y, it's whole numbers. Now, first of all, to make this reaction go faster, you're going to heat this with a Bunsen burner if we were face to face. And the reaction we're going to use is magnesium, reaction 1, plus oxygen gives, and I'm still not going to tell you what it is, magnesium oxide. Now, just a quick thing. Well, maybe not that quick. You'll be using magnesium metal. Now, these are turnings. You'll actually use ribbon if we were in a class. And notice how that's nice and shiny. And magnesium should be nice and shiny because it's a metal, and it can be shine because it has luster. All right, Spencer just said Zoom is lagging out. Let me ask, give me a thumbs up if you're having problem with Zoom and me. All right. Thank you for letting me know. I guess it's better now. That could be you, could be me. I've got a new modem router, and usually my internet service has been pretty good. I should keep my mouth shut. I think it was last summer because I had an old modem that was going bad on me. Twice during a lecture, I lost my internet. Oh, that was frustrating. Anyways, magnesium metal is a shiny solid. Now in this lab, what we're going to do is heat up magnesium in a crucible. It's quite awesome to do. And it's also dangerous because it gets very hot, over 1500 degrees Fahrenheit. Yes, that hot. And you react to make magnesium oxide. Now, in the air, we're burning this as oxygen, but there's also nitrogen. And nitrogen can react with magnesium to form magnesium nitride. Now, good news, if you take the magnesium nitride we make and react it with water, you'll get magnesium oxide and ammonia, which is a stinky gas, a dangerous gas. One of my less fond memories is on a summer day, I was at this one chemical plant. I was asked to help out. I supervised unloading a railroad car, about 250,000 pounds of liquid ammonia. And I was in one of those hazmat suits with the face mask and an air tank on your back. And when it's 90 out and the humidity is high and you're sweating, and if you break the mask to wipe the sweat out of your eyes, you're dead. It's not a fun time. By the way, I survived, in case you were wondering. All right, so you'll also need to know that you'll be adding water at a certain point to get rid of and react any of the magnesium nitride to magnesium oxide. Now, in this lab, you'll determine the empirical formula of magnesium oxide, which means you have to determine what X and Y is here. Now, remember, 1 mole of an element equals the atomic weight in grams of that element. In order to determine, you'll use this knowledge to determine the empirical formula of magnesium oxide. And now let me do a YouTube video for you. And you would have been doing. Thank you, Ruben. I don't know if you've ever smelled ammonia in large concentrations, but it'll knock you off your feet, literally. But anyways,
Grammarly does more than catch errors.
Time for commercial. Commercial over.
For magnesium oxide. You'll do this by combusting magnesium in an oxygen-rich environment. To begin, you will need to determine the mass of a crucible and its lid. Make sure they are both clean and dry before you weigh them. Once you've recorded the weight of the crucible and the lid, add in the magnesium ribbon and record the combined weight. The weight of the ribbon should be about 0.5 to 0.75 grams. Do not wrap the magnesium ribbon too tightly. Air needs to get in for the reaction to take place. When lighting a Bunsen burner, ensure that anything flammable such as hair or clothing is well out of the way. Turn on the gas flow and then bring a lit match or lighter towards the end of the Bunsen burner and it should ignite. In order for this reaction to proceed properly, you need to make sure the Bunsen burner is close enough to the crucible to heat it well. The high temperature will cause the magnesium to ignite, though first the crucible will begin to glow with the heat. Raising the lid of the crucible will allow oxygen from the air to enter the crucible. This will ignite the magnesium, causing the formation of magnesium oxide. Do not look directly at burning magnesium. The intense light can damage your eyes. During this reaction, you will want to ensure that oxygen gets in for the reaction to take place. You can either do this by tilting the lid off the crucible slightly to allow oxygen flow, or raising and lowering the lid periodically. Be sure not to let the reaction smoke too much. Any smoke coming out of the system is actually a loss of product. Allow the reaction to proceed, periodically checking on it to see whether or not ignition occurs when the lid is raised. When ignition finally ceases, you know that the reaction is done. At the moment, you can see that this is still glowing hot, but no ignition is taking place, so we know that the reaction is done.
Magnesium
Turn off the
oxide.
Bunsen burner and leave the crucible to cool. Allow it to cool completely before proceeding with the next step. Using a medicine dropper, add a small volume of water to turn the solid in the bottom of the crucible into a thick paste. You'll do this by stirring it up with a glass stirring rod. Ensure that all the material remains within the crucible, so wipe off the stirring rod on the edge of the crucible before you complete this step. Return the crucible to the Bunsen burner and heat it once again. This will complete the formation of the magnesium oxide. This process will take several minutes, but you can check on it periodically, and once it is all light gray color, the reaction is complete. After the drying process, allow the crucible to cool before weighing it. Make sure that it is cooled completely before you proceed with this step. Obtain and record the final mass of the crucible and the solids within it. Finally, clean and scrub the crucible to remove any of the solids to ensure that it's completely clean before returning it.
All right, couple things. You see that white solid almost looked like cigarette ashes? I have to say, I used to be a heavy smoker. I was addicted to cigarettes. Luckily, I gave it up a long time ago, back in '85. Otherwise, I'd probably be dead by now. Killed my father, unfortunately. But anyways, that's the magnesium oxide. Remember when they put the water in there with the eyedropper? That's to get any magnesium nitride reacted to magnesium oxide. Now, one of the things we never do is mix it with a stirring rod. You don't have to. Just put a few drops with an eyedropper and that does it. This is a fun lab too, but dangerous. That white light, it was red hot, beyond red hot. And that cover, if you're not used to using the tongs, the crucible tongs, sometimes students will fall off. And I've told students when we do this in the lab, I keep on repeating, that cover falls off, don't try and grab it like this, catch it. Oh, one year I had a student do that, and she did it, went like that, and still has second-degree burns right here. Mother was a nurse, called me up, got my phone number from the school. Boy, was she mad, and I could understand that. And I said, I'm sorry what happened to your daughter. We got her proper medical attention, but she still had a bad burn on her hand, which was not comfortable. And I told the mother that I kept on telling students, don't, if it falls, let it break. You can do the experiment, it's quick, and don't injure yourself. And when I asked the student afterward what happened, she said, I remember what you said, but I just I did it. I don't know why. And she told her mother that I had warned them. And then her mother apologized. And I apologized to her mother that I should have done more, but there's only so much you can do in a lab. All right, let's get back to this lab. Here's the same experimental procedure. Since we're not going to do it at home, no. I give you the weight of the crucible and the magnesium in the cover, number 1. The weight of the crucible and cover empty, number 2. And the weight of magnesium, which is number 3, is number 1 minus number 2. You've got to do this. Let me do something. You've got to calculate that. Next, from the final data, you have the weight of the crucible, the cover, and the magnesium oxide. And you choose the original weight of the crucible and cover empty, number 2, and the weight of the magnesium oxide, which you have to calculate, which I call number 5, is number 4 minus number 2. Now, you have to determine what's the weight of oxygen atoms. Well, I call that number 6, and you take number 5 and subtract number 3. Next, you have to determine the moles of magnesium. Use number 3 that you calculated up here. The magnesium weight. Where did I hide it? And right here, equation A. The moles of, say, magnesium is the weight of magnesium divided by the atomic weight. Oop, that should be a T there. I missed that. Anyways, I told you I wasn't perfect. Now you know, of an element. And that gives you the moles of magnesium. And you're going to also have to calculate the moles of oxygen using the same equation A and this answer right here, number 6. And now you'll have the moles of oxygen atom. Now it's important, this is oxygen atom, not O2. This is important, it's oxygen atom. You want the atomic weight of oxygen atom, 16.0, to use in that calculation, not O2, 32.0. Now, here's where students get confused. Listen carefully. Divide the moles of magnesium. What?
Oh, you're not screen sharing right now.
Oh no, somebody should have yelled at me. Now do you see it?
Yeah.
Sorry, let's go back, instant replay. Did you see any of this? All right, let's go back and do it again. You'll get the weight of magnesium from this calculation, number 1 minus number 2, which give you the weight of magnesium, which I call number 3. All right, next, you'll get the weight of the magnesium oxide by taking the weight of the magnesium oxide crucible cover magnesium oxide, number 4, and subtracting the weight of the empty crucible, number 2. 4 minus 2, number 5, is the weight of magnesium. Now, weight of magnesium atoms are number 6, which is number 5 right up here, minus number 3 right here. All right, now to calculate moles of magnesium at an element, use equation A, which is this right here. 1 mole of an element equals the weight of the element in grams divided by the atomic weight of the elements in grams. And where do you get the weight? Number 3. You'll also calculate the weight of atomic atoms, which you use equation A, and number 6. 6 is the grams of oxygen atom, and you use this same equation. So now in 2 and 3, 2 is moles of magnesium, 3 is moles of oxygen atom. And for number 4, divide the moles of magnesium, which is the answer to calculation 2. That means right here. Divided by the smaller number that's in calculation 2 or 3. And this is important. You round it off to the nearest whole number. X and Y are exact numbers. You can have a fraction or decimal. And that number will be X in this formula. And then for number 5, divide the moles of oxygen, which is from calculation number 3, by the smaller number, again in 2 or 3, and important, round it off to the nearest whole number. And this is the Y in MGXY. And now what you have to fill in is put in the number you have for X and Y and write the formula right there. And then you know what's coming up next. Yes, questions to answer. And you only have 2. Now, one thing I got to change, I don't think I did it right in Blackboard. A week from today, if my memory serves me right, come on, serve me right, is in-service day for teachers at COD, which means you don't have any class or lab a week from today. Labs are always due the next lab period. So since we're not going to have any lab next week, you now have 2 weeks to do this lab. Now, if you're having problems with it, always feel free to come to my office hours. And with that, I'm done for today. I hope you all have a nice rest of the day. Gain gesund, be healthy. Bye now. If you have any other questions, I'll stick around.